This morning, I want to highlight some of our historical contributions in celestial mechanics and also our modern contributions in celestial mechanics. We know a lot of space mechanics is essentially directly derived from data. And there's a lot of historical references to Kepler, etc. If you're interested in more of the treatment, I have a lecture tomorrow about it. So please come by. But more modern celestial mechanics and what we now know as geodesy is also founded from space technology. And the Center for Space Research at the University of Texas at Austin has been a pioneer in that area. And the first aspect of the panel discussion today is about introspection, how we have used space technology to learn more about the nice, beautiful planet we live in. And to help us learn about the salient aspects of that, we have our first panelist, Dr. Srinivas Betadpur, who is the director of Center for Space Research. He has worked on several missions, including what I consider the modern engineering, space engineering marvel, GRACE. And Dr. Betadpur is here today to talk about some of the key contributions of space technology for planetary sciences. To lead off the discussion, I have a question for Dr. Betadpur. Data has been at the center of astrodynamics, as you know very well. Could you elaborate on the GRACE mission and how it has impacted satellite geodesy and data-driven planetary science?
Thank you very much, and thank you for giving me this opportunity to speak to the audience about a subject that has been near and dear to my heart for about 25 years now. And and I think the Space Week event in data science conjoined with the Space Week event at A&M, this is a beautiful program for the entire week. And I am watching with envy. It is very well done, and it covers a good amount of ground that gives the next generation exactly the right view of how the two very important disciplines, growing space enterprise, particularly in this part of the country, and data sciences, which is, of course, of global interest, how the two come together. And so my congratulations to the group at A&M for having arranged this event. And I thank you all for having invited me. And I think, as Maji already alluded to, data sciences for us pretty much starts with Kepler, who obsessed about, what was it, about 10 arc seconds left over that he could not explain in the observations for about 20 some years. And we got Kepler's laws and celestial mechanics out of it. And so physics has always advanced in that fashion. And it has been a bit of work for me to understand how data sciences fit into our discipline. And I'm not there yet. So I'm not there at the point of having actually made contributions to data sciences, but I'm certainly an eager user of the data sciences. And there are two or three aspects that I thought I would talk about that specifically touch upon the data sciences and engineering, actually, because engineering, physics, and data sciences, they are not separated for us. So I will share screen. You can see the screens. Right. So let me talk a little bit about the impacts of the GRACE mission. Maji, this is all good?
This is all good. When you project, could you use the presenter view?
It's not presenter view?
No.
Okay. All right. So for me, it is showing presenter view. Let me see why for you it is not. There we go.
Click swap displays on the upper left.
Yes. And I am on the wrong screen for that. How about now?
Fantastic.
Okay, cool. So sorry for the slight disruption here. A quick survey of the impacts and why it matters. This actually brings up an interesting point for which I don't yet have an answer. So here, these are some things that have come out of GRACE. Long wavelength measurements of the Earth's gravity field have actually allowed us to do one of the best verifications of the general theory of relativity. And this is about a 2% precision experiment and uses satellite laser ranging data. And actually, recently there have been papers published about using 2 satellites orbit determination. This is the core of what we teach in celestial mechanics and at both UT Austin and at Texas A&M. And the orbit determination skills that are very much an aerospace engineering skill. And it used gravity field models derived also using the same aerospace engineering skills. And the funny thing is actually the physical principles that we are using for both deriving the gravity field as well as using it for verification of general relativity, basic principles, not the general relativity, but the basic mechanical principles were already established by Newton. So one might joke that all that has improved since then is technology and the computers. This is another view of great social significance. What you see here is calendar year on the x-axis, and on the y-axis, you see the global mean sea level, the total sea level relative to a reference frame fixed to the solid Earth, roughly speaking. And this is of interest because this tells us a lot about the climate and how it is changing. There are 4 curves on there. And the blue curve tells you what this measurement of the sea surface height altimetry is telling us. A good, by this time, more than a nearly 30-year record. Actually, the technique itself is about 50 years old by now. And so that's the height of the ocean, and the orange is the mass of the ocean as measured by GRACE, and the red is the variations in the salinity and the temperature of the oceans as measured by a network called Argo. And the black is an attempt to close the budget between 4 different measurement systems. And the fact that we can do this is a pretty extraordinary achievement. And this is like about 3 decades of data science is built in, not at the volume, perhaps, that the modern data sciences deal with petabytes and so on. But the interesting part here is that each piece of data has been curated pretty carefully. And so one of the nice things about the NASA data as it heads into the terabytes and exabytes, for example, is that this is very finely curated, well calibrated, and well documented. And the documentation and data are released in a very controlled fashion. And that is what allows us to make these conclusions about fairly significant conclusions of societal significance with some confidence. I haven't yet wrapped my mind around how data sciences, I was looking at the IBM definition of data sciences, and it emphasizes the use of AI and ML, and we understand that is the main theme this week. I haven't yet wrapped my head around coming from the old-fashioned data analysis viewpoint that relied on well-calibrated and well documented data sets. What challenge that presents, I think in some ways, perhaps I can leave this open for conversation. The formalism of data sciences are perhaps ahead of the quality controls of the data sciences that they are intended to operate on. Usually I hear about this in the sense of labeling, for example, of images or of training data sets. But it gives me a feeling that there's something more than just labeling that is of importance. The calibration, validation, and documentation of the data is pretty massive effort. And this is an example of great societal significance arising from spaceborne observations. That is, I think, a good use case of the importance of getting that right. And so these are just another example of nice achievements of GRACE, which is that 4 different techniques. All of us tell the same thing about what's happening to the ice sheets in Greenland and in Antarctica. And the accomplishments, so I'll use this as the last page. There are many science accomplishments. Oddly enough, when we wrote the original proposal for GRACE in 1996 or so, we pretty much predicted all the phenomenology that we thought we could observe using the GRACE observations. And so we should make a distinction. It's not a hypothesis testing mission. It was a mission for actual measurements of a process that we, in physics, we knew existed, but there had been no previous measurements of it. And so the utilization of gravity as a means for measuring mass change was the innovation. And biggest outcomes have been from sustained, high quality, and continuous measurements from a hardware that is well controlled, if you will, or well calibrated to give you some confidence that the measurement 5 years from now is the same as the measurement today. All right. Let me stop share on that, because there are a couple of other points to make that touch upon data sciences insofar as the space missions are concerned. And I want to show you a spectrum of the signals that can be measured. So these are, there are many different measurements you can make from space for measuring mass change. And one of them is gravity gradients. And the gravity gradients are the second derivative spatial rate of change of the potential, or the spatial rate of change of the gravitational acceleration. It has information about the gravity field and therefore the mass change. And this is sort of a student exercise of calculating the gravity gradients. And you see the two labels YY and ZZ. For those of you that are spaceflight mechanics, familiar with spaceflight mechanics, you'll understand cross-track and radial. But for the conversational point, the directions don't particularly matter. What matters is this. Look at the x-axis, which is frequency in units of cycles per revolution. And so the 10 to the minus 3 approximately corresponds to about 50 microhertz on the left side. And on the right side, you have 100 cycles per revolution, which roughly corresponds to, let's say, a few tens of millihertz. Right. And so this is about 4 to 5 decades in frequency range. And an instrument engineer who looks at this generally cringes, because this is not an easy achievement to derive an instrument that is actually stable across these long frequency, the wide frequency ranges. But that's what the potential measurement requires. And that's what is unusual about this, that the engineering of it and the data has attributes, has signal content that is spread across such a wide frequency range. I'm not sure how to look at it from the data sciences viewpoint, because the ideas such as classification or identification of motifs and so on, they seem to be well evolved in the data sciences domain. I haven't seen too much conversation. And by the way, again, I would be glad to hear from experts if there are actually methodologies that assure that the information content that is being extracted from these observations can maintain its integrity, if you will, across these wide frequency ranges. Let me show one more, and I think I'm kind of pushing my time allocation here before I should make room for conversation, but there is one other diagram I want to show. This is the second aspect of the data as we see it from space. So here, x-axis is frequency in hertz, y-axis is square root of the power spectral density, as you might typically define it in units of signal per square root hertz. And red are actual observations from GRACE satellites. So typically, if you looked at the numbers coming out of the gray satellites of the distance between the satellites, you see a kilometer variation, plus and minus a kilometer variation in range. And you see meters per second variation in range rate, or you see a millimeters per second square variations in range acceleration. So that's the total observation that the instrument is putting out. We do know a lot about the Earth. We do know a lot about the gravity field variations. And so I can take that knowledge and actually account for about a few parts per million. And that's the difference between the PSD on the red and the PSD on the blue. So I take the red and remove from it everything I know about the planet. We do know a lot about the planet. And I take the residual and make a PSD of it, I get the blue. And that's parts per million. And then all new science that you are seeing is actually contained within the blue and the green curves. The green curve is the residual after I have extracted the hydrology or the ice mass changes or the atmospheric variability or the oceanic changes that we did not have measurements of before. So all the innovation, the new science that has come from this data lies somewhere between parts per million of the observation and parts per billion of the observation. So my students, we are experimenting with the use of the AI and machine learning. What we find is actually in the bulk, the data collected from spacecraft actually lends itself very well to simple models such as the CNNs or the LSTM. I knew what the acronym LSTM stood for, but I'm sure some in the audience will know this. It's interesting how well it replicates it, but it's not clear if it replicates it at the parts per billion. So one curiosity that I haven't yet found an answer to is that modern data science methods, how they hold up and how they allow us to get from the blue to the green, i.e. from parts per million residuals of observations to parts per billion residuals after the new science has been extracted. So these are some curiosities, the variation in scales, both in time and therefore in space, since we are traveling in the orbit, and variations in the orders of magnitude, and the levels of guarantees and quality assurance we require from data that have taken hundreds of millions of dollars to collect, and that are actually whose outcomes are of great societal significance. So I think those 3 points, it's my curiosity to see how the modern data science methods deal with or hold up with consideration on those 3. Okay, so I will stop there and open the floor for questions.
Thank you, Srinivas. Those were very good challenges, I think, for the data science community. I have a question while we are waiting for audiences. In the audit of the increase in the ocean mass, water mass in the oceans, which is a tremendous result, and also you were also studying the decrease in water mass from the ice, ice and so on and so forth. And in the process of that, you were actually able to assess the levels of drought in California and many other places in the world, in Bangladesh, and so on and so forth. Have those been closed, or trying to close the total mass of water? A type of a conservation law motivated the discoveries of the individual control volumes? Could you comment on that?
Yeah, so one attribute of the technique, the satellite to satellite measurement technique, is that there are a couple of modes of the mass distribution and distribution change that this technique cannot observe. One, we actually make an assumption that the global mass of the Earth is conserved. There is no external input or no meaningful external input, right? So there's conversation about ice meteorites striking and so on. So that's not believed to be of any great size. So that takes care, for those of you that know spherical harmonics, that takes care of the 0-0 harmonic. So the gravitational constant GM for the planet, which is typically determined from satellite laser ranging, which, by the way, was analysis done here at CSR, if I may show off
Yes,
some
please.
years ago. And that's a sort of a conventional constant. Then the center of mass of the planet is a mode, those are degree 1 harmonics that emission light grays cannot observe. And so for that, we rely on either models or we rely on satellite laser ranging to tell us that information. So setting that aside, you can at a gross level, you can balance the mass between land and ocean. So if you total up the grace estimates over land and you total them over oceans, the two balance out. They're in opposite phase and they sum to small numbers. That's one aspect of it. Second, the land component can be broken up into several parts, and some of that actually is due to ice and the other is due to river runoff. That partitioning is actually a little more difficult. The ice is easier because it is highly localized. It's easier in the sense it does take several years and several communities to do it, but the answer is a little more definite. One is that there are other techniques available, ice sheet altimetry like ISAT-2, synthetic aperture radar has given us ice stream velocities, surface mass balance models are giving us estimates of ice loss. That's actually a budget that closes, so people that are curious can Google IMBIE, IMBIE. There's a sequence of 3 studies where essentially ESA and NASA knocked heads together and says, we're paying a lot for these assets to make these spaceborne measurements. Let's just make sure that everybody gets at the same answer or consistent answer on what the ice sheets are doing. And so that activity has actually reconciled the ice sheet mass budget between different techniques. So it did require help from outside grays to get some assurance on that. That's typical. The land storage changes are more distributed. There are lots of multiple kinds of environmental physics involved in that. And so typically those budgets have been closed is a strong word for it. There is still a great deal of understanding that is being obtained, but those are typically studied in conjunction with the GRACE data conjoined with model outputs. And North America has wonderful models for land surface water cycle, land water cycle. Europe does, as you might all the generally richer in science funding, all those communities have some assets and some information, but vast swaths of the world don't. And so there it's a mix of ground observations and modeling such as it is available to close the budget. Interestingly, actually, community seems to have confidence enough in the GRACE observations to actually make policy decisions based on indications. Numbers don't have to be precisely correct, but the indications, if they're showing a decline or a rise or intra-annual variability, those indications seem to be enough, and this is a subjective opinion, for people to actually make decisions on the land water cycle. So it's sort of a piecemeal validation and utilization across the globe, depending on the domain.
Thank you, Srinivas. That was great. Would you, in the little time we have, comment on how some of the new quantum technologies that you're pioneering would impact GRC?
Yeah, thanks. Actually, so I'm not an atomic physicist. I just play one on TV. So this is a reference to a Space Technology Research Institute award from NASA STMD, Space Technology Mission Directorate, that we recently won. Effort started in November. And the intention there is to deploy quantum sensing technologies, which basically is the idea that the wave nature and the matter nature reacts to the ambient field, whether it is forces or it is inertial acceleration or it is electromagnetic fields. And the wave nature of it can be utilized to actually do precision metrology. The intention is, the advantage is supposed to be that atomic properties being fundamentally fixed, that you end up with instruments with long-term stability. And that goes back to the point what I made about 10 microhertz to 100 millihertz bandwidth of the instruments you desire. And so it's believed to be one solution. There's a long way to go to get to actually realize it. But that's what we do as exploration to see where this takes us. And so through inertial sensing, the idea is to measure gravity gradients and then utilize the gravity gradients in the same way utilize satellite to satellite tracking to infer the gravity field and the mass change. And so that is interestingly that instrument actually in our collaborators there are Jilla at the University of Colorado Boulder. And in fact, they do have a concept for instrument sensing using machine learning. The information as it passes through the quantum sensing instrument is dealt with in the sense of machine learning. So the instrument configuration, if I understand that right, I hope I'm not butchering their intent in this, but essentially the way my colleague put it is that if you want a good gyro, you tell the instrument, be a good gyro, and it becomes a good gyro. And of course it learns and it adapts to be a good gyro. So they're much more definite about it than I am about my children, for example, to learn and adapt. I see there is a question, perhaps. I don't know if that was an answer to your question, but yeah.
No, that was great.
Yeah.
Ram, would you like to ask a question?
Yes. Professor, there is a speak of frequency spectrum graph from the measurements and the model you mentioned in the last graph. So the residuals in that, is it an absolute difference in the samples, or what are the residuals, post-fit residuals? What do they
those are
correspond?
post-fit residuals. You solve a linearized least squares estimation problem with a certain observations. And after you have fit estimates, you project the fit estimates back to the observation space and you subtract the original instrument observation from what you were able to fit into the estimated parameters. And the difference between them is the post-fit residual. I'm not sure if you use the same language in estimation as we do here, but the post-fit residual, if that is familiar, that would be the right phrase to use there.
Okay, great. And you mentioned, can you expand a little bit on the parts per million versus parts per billion distinction in?
So yeah, let me put up the, well, okay. The total observation is of the range of plus and minus 1 kilometer in the, sorry, is of the size of plus and minus 1 kilometer in the distance between the two satellites. And given what I already know about the planet, its gravity field, non-gravitational accelerations, and the physical models for orbital motion, I can stick that into my software and predict the observations to about millimeters in range.
Okay.
And so that's the part per million reference that I can already explain away parts per million of the observation using mathematical methods and physics models and parameter models that I already have from, I mean, we have spent centuries studying the planet. We know a lot about it. And what we know can explain away the observations to parts per million. What we innovate, what we search for new is on the order of parts per billion underneath that.
Great. Thank you.
Yeah.
Thank you, Ram. Thank you, Srinivas. This was fantastic. Let us now focus on, so let us move on to exploration and to discuss the latest frontiers in exploration. We have the distinct pleasure to welcome Dr. Diane Davis, who is the mission design lead of the Lunar Gateway program at NASA JSC. Dr. Davis, we are very happy to report that she's an Aggie. She received her BS in physics from Texas A&M University, MS in astrodynamics from University of Texas at Austin, and PhD in multibody astrodynamics from Purdue University. Previously, Diane worked on interplanet navigation group at JPL and mission ground control system development at JSC. Research focuses on orbit maintenance and dynamics of departing flow in the near rectilinear halo orbits. Diane, welcome. Thank you for
having me.
making time for us.
I'm very happy to be here. Thanks for inviting me and letting me speak to the data sciences group.
Could you elaborate on what your responsibilities are in your current role and the excitement with the Artemis program?
Sure. So let me share my screen. All right, and head into presentation mode. How does that look?
That looks great.
All right. Okay, so I'm working on the Gateway program. So what we're doing, we're going to build a space station around the moon, which is super cool. And so the components are already in construction on the ground and will be launched here in a couple of years. So we're putting a space station out there around the moon in a relatively large orbit. It's a bit different than the Apollo program. And I lead the mission design team. So what is mission design? We do a lot of designing of paths in the space. So we want to understand the path that the gateway itself will travel, and also how we get there. So where are we going in space and how do we get there? How will Orion bring our astronauts out to the gateway to visit? How will our logistics modules, you see a logistics module here, either arriving or departing. I don't think my mouse is showing, that's okay. Either arriving or departing from the gateway. So they're going to bring up supplies, air and food and water and equipment, for example. So how do they get to the gateway out in space around the moon? And then our gateway lifetime is 15 years, nominal lifetime. So initially, we're building to requirements to make sure that we can last up there for at least 15 years. So how do we stay there? We're going into an unstable orbit. So how do we make sure we don't leave? And then how much fuel, how much propellant do we need to make sure that we stay in orbit for 15 years? We also need to be able to point our antennas at the Earth, and we need to be able to point our solar panels to the sun. And then we have to also satisfy constraints of other spacecraft who may not want the sun on certain sides for heating constraints. And so we need to make sure that we're pointing the spacecraft in a good direction. And then we do, some of what Srinivas has been talking about this morning is how do we figure out where we are in space? So how do we do our orbit determination? And then how certain are we of that location? We're certainly not going to know our location to parts in a billion out here at the moon. However, we need to know where we are so that we can make sure that we're in the right spot. And then one thing that I've been looking a lot at lately is where do we go after we leave the gateway? How do we depart? So we have this big orbit and we can depart anywhere around the orbit in any direction and at any magnitude of delta V within constraints. And it's a chaotic regime. So this is an unstable orbit where a tiny change in your initial state will lead to huge dispersions in where you end up downstream. So part of the interesting sort of big data problem we've been looking at here is how do we figure out, with all these hundreds of thousands of possibilities for how to depart, which one is going to get us to where it is that we're trying to go? So that's what my team does. So I'm leading this team. We're looking at lots of things. It's pretty fun.
Thank you, Dan. That was fantastic. Could you help us sort of make distinctions between the gateway and other aspects of what you're studying, and its role as a staging location, and contrast it with what we did in Apollo? How is it different in various aspects? What are the fundamental and philosophical changes, especially in terms of the approaches to orbit about the moon, essentially?
Sure. Okay, so let me back up and just start with what the Artemis program is in case folks in the room aren't quite familiar with it. So, Artemis in Greek mythology was a twin sister of Apollo. And so they've selected the name. This is a moving on from the Apollo mission. So we're going to go send humans to Mars. And so this is a big program with lots of different goals and lots of different components, including the Orion crew vehicle, the SLS launch vehicle, the human lander system that's going to take folks from orbit down to the surface of the moon. And then also the human mobility program, which is going to drive astronauts around on the Earth. And then a whole new spacesuit generation program. So there's lots of folks working on lots of pieces here. And Artemis has already begun. So I'm sure y'all heard about the Artemis 1 mission that launched a couple of years ago. So it was the first human-rated spacecraft that headed to the moon. I mean, it was a test flight, an uncrewed test flight that went into a distant retrograde orbit around the moon in 2022. Additionally, Capstone spacecraft is a CubeSat that's gone up to the orbit that the Gateway is going to live in. It's called a near rectilinear halo orbit. So a really big orbit around the moon. I'll show a picture in a minute. But as we move on, Artemis 2 is going to launch here next year with the first humans to orbit the moon in the 21st century. So we've got a crew of 4 that's going to head up on Artemis 2, fly around the moon in an orbit similar to what Apollo 8 did, and then head back to the Earth. And then Gateway is going to launch. So this is the spacecraft that I'm working on. And it's going to welcome Orion and the crew to Gateway. So here's our spacecraft. It's going to be built up in space, much the way the space station was. And it's going to be in a lunar halo orbit. So this is an orbit that depends on the gravity of both the Earth and the moon simultaneously. So a really big orbit. It's constructed of a bunch of pieces. And one area that Artemis has progressed on from Apollo, I would say, is that it's a huge collaboration between different countries and different corporate partners. So Maxar is building the first element of the Gateway, which is the power and propulsion element. It's there with the solar panels, and it's going to provide our power, and our thrusters, our propulsion. And Northrop Grumman is building our second piece of the Gateway, the habitation and logistics outpost, which is like a habitat, right? It's the living space for the astronauts. And then we have an airlock. We have an Esprit refueler module that ESA is building. It's going to hold our windows. The UAE is going to be building our airlock. And you see the Orion crew vehicle. It's a NASA program and also ESA, built by Lockheed Martin. We've got HLS. You see the government reference lander there. But in fact, for the first 2 missions through Gateway, SpaceX will be sending Starship up. And Blue Origin will be sending a Blue Moon lander up. So it's pretty exciting. So these guys, they're gonna launch planned still in 2025 on a Falcon Heavy rocket. So these guys are gonna go up first, and then Artemis 4 is gonna come to the Gateway. And so we got 4 crew are gonna launch on SLS and Orion, and they're going to bring up our International Habitat module that's being built by ESA and JAXA, and then Starship is gonna dock with Gateway and send 2 of the astronauts to the lunar South Pole, and they're gonna spend a week there. So on Apollo, we did not spend quite so long on the moon. So, but the way our orbit works, we're going to spend a week on the moon. Srinivas, did you have a question? Oh wait, you're muted. I can't hear you.
Sorry, I didn't mean to interrupt you. That is hand raised. Just I will wait until you're finished with the point. Yeah.
Nice. All right, I'll call on you first. So Artemis 4 is the first mission, and it's going to look something like this. So Orion is going to launch from the Earth, and about 5 days later, they'll do a powered flyby of the moon. And then a day after that, they'll insert into our NRHO. And then they'll do about a 12-hour descent to the lunar surface while the Gateway hangs out in orbit. And after the astronauts stay on the ground for about 6 days, we'll do an ascent up to NRHO. And it takes, again, about 12 hours. And then the astronauts will climb back on Gateway, hop back in Orion, and Orion will leave. And about a day after orbit, they'll do a powered flyby on the way home. And then it'll be about a 4-day trip between the moon and headed back home. So this is what the orbit looks like. They'll land off the coast of San Diego. But one thing that's really challenging for the Artemis team, and this is not my team, in fact, let's play that again, is that for every moment along this orbit, I mean, we have the nominal trajectory, right? And we have a nominal trajectory for every second in our launch period. But then for every moment along that trajectory, we have to know how to get the astronauts home if we have an Apollo 13 moment, right? And so 90%, 95% of the trajectory design work done in preparation for this mission is to understand the aborts. And you've got a chaotic regime. You've got the gravity of the sun, the Earth, and the moon all acting simultaneously. Which means that Kepler would be a little bit lost. We've got a lot of gravitational bodies now. And so managing the design space, coming up with the initial guess for your optimizer, and then managing the huge quantities of outputted data it's a big issue that's, I would say, still unsolved. So I think that there's a lot of real estate and opportunity for the data science field to help out us astrodynamicists understand how do we manage all this data that we are generating. Let's see. So then after Artemis 4, Artemis 5 is going to show up. This is a rendering of the Blue Moon lander. And so we're planning with 2 different lander providers. So that's always fun too. So we got SpaceX going to land for us on Artemis 4 and Blue Moon on Artemis 5. This will also be the first mission that uses the lunar terrain vehicle to drive around. So that'll be pretty fun. So going back to the differences between Artemis and Apollo. So when Apollo went, they were individual missions that achieved a purpose and came home. In Artemis, the goal is to establish a sustained presence on the moon. So sustained human presence. So not only these individual missions, but simultaneously, we've got other landings going on. We've got cargo landers, we've got a big rover, with the goal of sending 4 astronauts to the lunar surface to stay a month or more out in the future. So sustained human presence, and then, the goal is to build a habitat on the surface that will support long-term presence on the moon. So we're going to stay is the NASA tagline. We're going, and we're not just going to go and come back. We're going to go and stay, and we're going to hang out on the moon for a good long time. Another difference with the Gateway is the orbit that we're going to. So this is the low lunar orbit that Apollo went to, or similar to it. It takes about 2 hours to go around the moon and stays about 100 kilometers from the lunar surface in a circle. This is actually the Korea Pathfinder lunar orbit. This is our near rectilinear halo orbit. It's really, really big. It gets 70,000 kilometers from the lunar surface at its furthest point, and it takes a week to go around, almost a week. So you can imagine you're looking up at the moon, the thing's going to take up just about the whole sky. And the gravity, especially of the Earth, affects the orbit so strongly that it pulls it out of elliptical mode. So this is a non-Keplerian orbit entirely. So you can see how it doesn't look like an ellipse at all in the inertial view that you're seeing here. So that complicates the trajectory design, but it also offers significant opportunities. We have a lot of things that we have to do. So what complicates these orbits is that they're highly sensitive to perturbations. And we have an enormous data space, as I mentioned earlier. So anywhere along this orbit that you do your maneuver, and in any direction, you can see here a departing trajectory. And we have to be able to understand which of the initial states will lead to what we're looking for. So we have no analytical solutions because Kepler has been left behind. We have, so we need innovative design methods, and we look for finding needles in the haystack. Now, one reason this orbit is great for us is we have a lot of stuff to send to the NRHO, right? It's going to be a way station for Orion, for logistics modules, for vehicles heading on towards Mars. And what you see here is a representation of the gravity wells around the moon. And you can see where the low lunar orbit that we just saw sits at the very bottom of the gravity well, whereas the NRHO sits at the very top. So one of the main benefits to this orbit is that it's cheap. It's relatively cheap to get in and then to get back out. And so when you're sending Orion and you're sending logistics modules and you're sending Mars crew vehicles to hang out at the Gateway before they go on to their final destination, it makes sense to send them to the top of the gravity well and not send them all the way down to the bottom, where then you have to spend a ton of propellant to climb back out again. So in addition, the gravity works in these orbits. It's one of the halo orbits. It's a member of the halo family. So if you've heard of the James Webb Space Telescope, it orbits in a Sun-Earth halo orbit. This is a different member of the halo orbit family, and this is one of the Earth-Moon halo orbits. But similar to the moon itself, the way the moon always shows us its front side, it's tidally locked with the Earth. The orbit is as well. So when you look on the left, you're looking in the Earth-Moon rotating view. So in this view, the Earth and the moon are holding still. So if you're standing on Earth and looking at the moon, the orbit is always making a halo around the moon, which means that we have constant line of sight to our spacecraft. It's never going to go behind the moon, so we can always communicate with it. And then when we're putting astronauts on the lunar South Pole, we spend, so it's a 6.5 day orbit, and we spend about less than 12 hours over the North Pole. And so almost entirely, all the time we have a line of sight to the South Pole, and so we can communicate with our astronauts here. And I think I have one more. Oh yeah. So as I mentioned, it's an international collaboration. It's a collaboration with many commercial partners. And so the goal is to establish a sustainable presence on the moon in cislunar space. And so this is a list of countries that have signed the Artemis Accords, which is a discussion of responsible use of space, and particularly lunar space, so that we can sustain a presence out here and all have a peaceful time on the moon.
Fantastic. Any questions for Diane? I think Srinivas, would you like?
Yeah, but in these events, I usually stand back behind the students, but I can sneak one in while
Sure.
someone else raises their hand. You mentioned this. First of all, Diane, thank you. Those are absolutely so informative graphics, and your narration that goes along with it just makes it so clear. Thank you.
Thank you.
Several times you mentioned about commercial partners, right? And one of the unique things I have noticed over the last several years from news stories is that in this entire program, there is much greater emphasis on including not just data, but also actually inference and analysis from commercial partners in the whole enterprise. I'm curious if that has required some culture shift or some special measures to make sure that everybody's on the same page and is moving in the same direction.
Absolutely. Yeah. So you can see here, a list of folks, some of the partners that we're working with. And so, Orion has been built more in the traditional NASA model, where NASA is leading the development. They're in charge of the development, but the Lockheed is building the spacecraft, but it's still a NASA and ESA project. For going forward, for the power and propulsion element, for example, designed by Maxar, or the Starship lander designed and built by SpaceX, those companies are in charge. So they are delivering a spacecraft that will meet the NASA requirements, which is a different philosophy rather than NASA leading the development. And I would say it opens up a lot of opportunities. The goal is to get the commercial partners more involved, and also to use the efficiencies that the commercial partners bring so that we can achieve sustainable spacecraft within the budget that we have available. But I mean, there has certainly been challenges from my perspective. I think writing, I didn't appreciate until I started working on this, the challenges of writing requirements that say exactly what you mean, right? It's like when you rub the genie's lamp and you have to say your wish in a way that can't be misinterpreted.
Yes.
It's a very good
So
analogy.
writing the requirements so that they say exactly what you mean and that they mean the same thing to everybody who reads them is really hard. Yeah.
It is interesting. I was in a symposium here yesterday on AI and autonomy, and exactly the same question came up about whether the data science methods need to use language models to make sure, my syntax is different than your syntax. We might intend to say the same outcome, right? This is what you're saying, right? But you might express our requirements, the same requirement, or no, we might express the same intentions as two different requirements.
Right. And then read the requirement to mean two different intentions. So yeah.
That is definitely a data science problem. And well, okay, it's one of the challenges data sciences has to take up. Yeah.
Is there a question in the chat?
It's a comment that cross-discipline communication is a science in itself.
I think so, yeah. And then some, some of our partners have very different cultures as well, like an internal corporate culture. And I don't mean like international cultures. I just mean like a corporate culture at two different companies are so different. And so it's been fascinating to watch the interactions between them. And then we have the challenge where we can't share data between the providers because we have to protect proprietary information. And that also seems its own science as well. How do we communicate well enough so that we can all build a spaceship together without disclosing information that we're not supposed to disclose? So that's a challenge I would say is not as much fun as the challenge of figuring out how to jettison a spacecraft safely from our orbit. So.
Any questions from students? Come on, don't be shy.
I have a question, Dr. Mahdi.
Go ahead.
So Dr. Davis, you talked about, at least you mentioned the pre-return trajectories that Apollo 8 and that was necessary for Apollo 13. And you showed the departure from Gateway and the lunar flyby and burn to get back to Earth. Could you talk about what some of the contingency trajectories, I guess, look like if that burn is not nominal once we leave the Gateway, and what sort of the possibilities are if that doesn't go smoothly, I guess?
That is a fantastic question because that is a really hard problem. So Brian McCarthy on my team, he also works on the Artemis team, is looking into how to generate initial guesses. Hopefully he'll be at a conference in Denver this August speaking about that topic exactly. So there'll be eventually a paper on it that we can get to you if you're interested. But it's extremely challenging to do these. There's my mouse. So like you said, you've got the translunar injection out here at the Earth, and obviously that's important. And then you've got little correction maneuvers along the way. But this powered flyby is really big at the moon, and if you miss that, you're not on the right orbit, and then we have to figure out how to get home. And the same thing, this it's called NRI, the NRHO insertion maneuver, is also quite large. So those are both critical maneuvers. And if they're not executed appropriately, the trajectory looks extremely different. And so some of them like fly down here and then come back around to the moon like this to head home. Some of them do kind of backflips, for example, over the moon, but it's been extremely challenging from a data perspective to figure out, okay, you're here, how do you get back here? It's such a sensitive problem, you can't just target it with a simple targeter. So one of the methods that's been used is to try to simplify the design space using Poincare maps. So what you can do is take your trajectory, and then numerically you can spit off a ton of delta V's in various directions and propagate them forward and see where they end up. But if you propagate all the trajectories forward, you end up with thousands and thousands of squiggles on a picture that end up looking like spaghetti. And so you just can't sift through those. So instead, one of the methods that we use is Poincare maps, where you basically simplify every trajectory to a single point. And what we do is we might record where what is their closest approach to the Earth. And so you can, spit out your trajectories over here, mark which ones go close to the Earth, and filter out all your data to only keep those, and then understand what is the cost of that, what is the time of flight. And so when we're on a abort trajectory, we have to have enough propellant on board after whatever contingency has taken place to make sure we can get home. We might have more fuel than we expected because the burn didn't happen up here. We might have less fuel than we expected because too big of a burn happened. So we have to get home in the prop constraints, but we also have people on board, and they have a limited amount of time, survival time in the spacecraft. And it depends too, was there a breach in the spacecraft? So do they have air or not? Are they in their suits? Then you have one duration that you're allowed to get home. It's shorter. If you're in your spacecraft and everything is peachy, then you've got more time to get home. So it's a trade-off between how much prop you have left, how much time do you have to get home, and how do we get there? And so one of the big things that we're working on now is how to generate those initial guesses to feed into an optimizer in order to find the orbits, because there's an infinite number possible, to find the orbits that will get us home. So that's a great question. And it's been a really hard challenge, but we're making some progress. So it's really exciting.
Thank you, Diane.
Thank you.
that actually very interestingly also ties in with the navigation requirements. So how precisely should we know where we are and so on and so forth? These are all very important and intricate challenges.
Absolutely. Yeah.
Dr. Betadpur has to leave very soon. Thank you very much, Srinivas.
My apologies for stepping away sooner. Diane, it was a privilege to listen to you and to the material you presented. And
Likewise,
Majid,
Srinivas, thank you.
thank you. And thank you for arranging this. This was a wonderful opportunity.
Thank you. Thank you
Bye-bye.
very much. Bye-bye. I'm going to keep the Zoom alive for a minute or so if we have any other questions for Dr. Davis.
Hey, Dr. Maji, I have one.
Yeah, please.
Yeah, hey, Dr. Davis, this is Deep. So basically, this is about more related to proximity operations. So in ISS, we know that there is a keep out sphere, and then the visiting vehicles have the protocols. So how that will change when we talk about gateway? Is it same approach, or the orbit kinds of make it more complex?
That is another great question that's extremely timely and that we're looking at now. So for rendezvous, proxops, and docking, the RPOD process, they have very similar processes to ISS. So when you're in that close, and as long as you're not near Paraloon, up near the moon, we are moving very fast and the trajectory is very sensitive. And so we don't plan to do any docking up there. But as long as we're moving slowly out towards the bottom of the orbit, the RPOD process is going to work very similar to ISS with a keep out sphere and various gates to make sure that we don't crash into the gateway. But a more interesting question in my perspective is we're going to have various vehicles out in the NRHO loitering nearby. So for example, we're going to have a lander up there that's waiting for Orion to dock, and then everything will come and dock. But the lander will be out there first out in space so that it's ready to go when the astronauts come up. So where does it loiter, right? Where does it hang out near the gateway? So it's a more complicated question than an ISS. You've got a stable low orbit. Like if you know that what drag is going to do to your orbit, you understand what the perturbations will be. And so it's easier to design a safe location. Up in the NRHO, you've got multi-body dynamics dominating the trajectories. You don't have a predictable big force like drag up there. And so and you also have this chaotic regime where the trajectories out there tend to twist around each other in ways that we don't expect from our, low Earth orbit intuition. And so trying to understand what's the safe distance that they need to loiter and in what direction, in front, behind, side to side, do they go? That's another interesting question that we're making great strides, and we'll have some papers out about soon. And then there's multiple questions we're answering. What if we're loitering for an hour, right? Where do we stay? What if we're loitering for a day? Like we have a module that came and docked and then needs to undock while something else docks and then it comes back. There's some scenarios where this could happen. Well, if it needs to hang out for a day, we might know a safe place to put it for a day, but then what if it can't dock? What if it's going to stay out there for a week, a whole nother rev before it comes back? So those are two different safe locations. So which one do you use and how much does it cost? And then if you have a lander hanging out for, if we remember when Artemis 1 launched, that there were several launch attempts and several months in between them. And so a lander could be up there for as much as 3 months before Orion launches. So where does it stay for 3 months? That may be a different question than where it stays for 24 hours in one rev. So yeah, it's an interesting question, and we're working on getting all those answers.
That's a fantastic answer. Interestingly,
yeah.
Interestingly, a lot of things depend not only on the states, but also on the uncertainties. So it's very interesting.
Sure, absolutely. Yeah.
Have you been also considering micrometeoritic impact and other uncertainties? And I'm sure you are, but.
Yeah, the safety and mission assurance folks are certainly watching that and understanding the materials and what would be the effects and, the risk of a meteor impact, and, considering how debris avoidance maneuvers might work. You can't just do a maneuver and then have drag pull you back. you have to do a maneuver and then do another one to come back, or do a maneuver that will naturally bring you back. So that's interesting. And then how do we know where stuff is out there? We don't have a JSPOC up in the moon that we know of.
Great. So if there are no other questions for students, thank you very much, Diane, for the fantastic overview and amazing graphics and all the amazing work you're doing. This is really a fantastic time to be, to be a student and to be a professional working in space technology. And thank you for being a trailblazer.
Thank you so much for inviting me, and y'all, please come help us out. We need to understand how to deal with all our data. So come work for NASA. We can certainly use your insight.